Okay, welcome back to Real Analysis. We're going to continue our work in Chapter 2, looking at another theorem that you might be familiar with from calculus in Section 2.9 called the Monotone Convergence Theorem. Okay, so we'll start with some of our technical terminology. Got four definitions here. Let's kind of look at them one at a time. So if we given a sequence Sn, we're going to call that sequence increasing if for every value of n, the nth plus first term is strictly bigger than the nth term, okay? So a sequence is increasing if the terms are getting strictly bigger as you read out the list in the sequence. On the flip side of that, we'll call it decreasing. Sequence is decreasing if the nth plus first term is strictly less than the nth term for all n. All right, so the terms of the sequence are getting strictly smaller as n increases. Related to that is the notions if we allow, instead of the strict inequalities, if we allow less than or equal to or greater than or equal to, then the terminology that we're going to use is non-decreasing and non-increasing. So the difference is in a non-decreasing sequence, the terms are greater than or equal to the previous term. All right, so non-decreasing in the sense that they're not getting smaller. So they're greater than or equal to. Non-increasing is in the sense that they're not getting bigger. They're less than or equal to. And I'll leave it to your reading. The author kind of points out that this terminology is not completely uniform in all analysis books. Some analysis books use the word increasing for this thing that we're calling non-decreasing, and then they would call this strictly increasing and so on. But we don't have to make it confusing here at the beginning because we're only going to use sort of one set of terminology. So if I say non-decreasing, I mean that Sn is less than or equal to n plus 1. If I want to emphasize that that's a strict inequality, then I'll use the word increasing. Likewise for non-decreasing non-increasing and decreasing. Okay. If a sequence is any one of these four things, which it needn't be, a given sequence is typically not increasing, decreasing, or non-decreasing or non-increasing. But if it's any one of these four definitions, then we call it monotone, or sometimes people will call it a monotonic sequence. Okay, so I'm going to scroll back here just so you can kind of look at the word as I say it. So a monotone sequence is one of these four kinds. Okay, so if somebody hands me a monotone sequence, then it's either increasing or decreasing or non-decreasing or non-increasing. Cool, let's look at a couple of examples. I kind of squeezed in a little Desmos plot here. It's kind of small, but we can look at it anyway. I'll kind of highlight the example in the same color as the plot. So in the first example 1, I'm just looking at the sequence n. Well, that sequence is increasing. You can see it over here. The dots are plotted in red, and the output value is the input value. And you can see that those sequence terms are getting strictly bigger. Okay. The second example that's kind of drawn in blue in that same plot is the function whose sequence terms are the so-called floor of n over 2. So what's the floor of x? Well, it's the greatest integer that's less than or equal to x, where x is a real number. You proved that such an integer exists in your homework exercise 1.74. Yeah, you proved that given an x, there's a unique integer m. Let me just kind of write it to remind your brain of the terminology. Given an x, there was a unique integer m such that m was less than or equal to x, but x is strictly less than m plus 1. And this m is what I'm calling the floor of x. Okay, so my second example, my sequence here, the floor of n over 2, you can see it's a non-decreasing sequence. It's not the case that the sequence terms are always getting bigger. Here's the value when n is 1, and then n is 2. The output when n is 3 is the same as 2. They're equal. But then it gets bigger for 4, but then 5 is the same. I'll kind of let you think about why this is true. But that sequence is not increasing. But the terms of it are not getting smaller as n goes to infinity, so it's so-called non-decreasing. Okay, there's just a couple of examples. You can stop the video and make some more. Think about some of the sequences we've talked about and ask yourself, they might not be monotone at all, but ask yourself if some of our previous examples are monotone and what kind of monotone they are. third example, real quick here, I wanted to plot just again to remind you of a homework problem, but it's going to introduce or remind you of another term. So remember that homework problem about a sequence called xn, defined recursively by saying its first term is the square root of 2. And then starting with n equal to 2, the subsequent terms are given by the square root of 2 plus the previous term. Okay. You proved in your homework problems, well, 2.2.8 was assigned in the solutions I wrote. I also included the solution to 2.2.9. In 2.2.8, I believe that you proved that that sequence was bounded. Yeah, I'll just kind of write it right below here. You proved that I think all of its terms are less than 2. So it's a bounded sequence. In 2.2.9, it wasn't a homework problem, but you can look at my solutions. I included it. The sequence was proved to be increasing. That as you read out the sequence values, they kept getting strictly bigger. It was an increasing sequence. So this is a bounded increasing sequence. And I've plotted it here. I'm going to have to kind of scroll a little bit if you want to see my plot. Here I've just labeled the what the definition of the sequence is. And this sequence, I didn't plot this one on Desmos, I plotted it in Mathematica. So you can kind of look, it's very subtle that it's increasing because as n gets big, the values are not getting very much bigger. So at the scale that I drew this thing at, but what I wanted to draw this picture and kind of talk about, it appears, it looks like from this picture that the sequence xn converges. Yeah, the terms are getting strictly bigger, but it looks like it converges. I'm going to go out on a limb here, kind of pick a y value, draw it at y equals 2. It appears that the limit looks like it's 2. So I'm going to make kind of an irresponsible conjecture here based on this picture. I think that as n goes to infinity, this sequence looks like it has limit equal to 2. All right. So that's just kind of a, as I look at my screen, backing up a little bit, I did not draw my horizontal line very horizontally. I shouldn't make the video longer here, but I'm kind of going to fuss with it here. If I make that at 2 and I move it around, I'm wasting our time. There we go. Now it looks a little nicer. Okay, so you proved in your homework, even if you don't believe it by this picture, you know that none of the y coordinates on those sequence points are on that red line at 2. They're all less than it, but it looks like they're getting darn close to it. At the resolution of the screen, it looks like they're kind of even on it, but they're slightly below it, okay? So this monotone convergence theorem, I'm going to state it here in a second, but it says that, well, the reason this sequence has a limit is because, well, it's bounded and it's increasing, all right? And this statement about everything being less than 2, a little bit more is true. We didn't prove it in our homework problem, but 2 is actually the soup. It's the least upper bound of all of the values of that sequence. Okay, so stop the video maybe if you need to and let that sink in. I'm just going to kind of plow along here and state this monotone convergence theorem, which later on in notes in your homework as well, we can kind of just use an acronym. It's an important named theorem. We can just call it the MCT for monotone convergence theorem if you want. Okay, so what does it say? Well, it says if you take a monotonic sequence, so remember what that means. A monotonic sequence is either increasing or decreasing, or non-decreasing and non-increasing. We don't know which one, but it's one of those 4 flavors, I like to call it. So that's what our assumption is that we have a monotonic sequence. And then the theorem is saying that the sequence is convergent if and only if it's bounded. The sequence is convergent if and only if it's bounded. All right. We don't really even have to worry about the only if. It's already proved. I'm just going to write that here instead of putting it formally. We've already proven, or sorry, not the only if, maybe, I don't know if it's the if or the only if, but let me just make a remark above, right below the theorem here. Too late to stop this video and start again, so I'm going to give you the unedited version. But we've already shown that if a sequence is convergent, it's bounded. Okay, that was previous work. So that's already been done. So really, all I'm going to include here is a proof of the opposite, the converse inclusion, that if you take a monotonic sequence that's bounded, then it's convergent. Or as the author says, a little bit more specifically here, and then I'm only going to include the proof of part one, so let me just kind of walk you through it. If you take a non-decreasing sequence, okay, so that's a very specific kind of monotonic, then it's either bounded or, and the author gives us the answer, it converges to the soup of its values, or it's unbounded, in which case it diverges to infinity. Okay, so that's actually the statement we're going to prove. We're going to prove that if you take a non-decreasing sequence that's bounded, that it converges to its soup, and if it's not bounded, it diverges to infinity. On the flip side, and I'm going to leave it as an exercise to you, if the sequence is non-decreasing, then if it's bounded, it converges to its inf. Otherwise, it's unbounded and it diverges to minus infinity. Okay, but I'm going to leave that part to you. That's what we're going to prove. So I just said that we're going to prove part one and leave part two to the exercise. So let's introduce some notation. So let's take our sequence Sn, and let's suppose that it's non-decreasing. That's our hypothesis about it. Okay, and then we're going to kind of look at the cases of whether or not it's bounded or unbounded separately. So let's just give a short name to the set of its values. Let's let E equal the set of Sn, where n goes over all natural numbers. So it's the range of the function S, if you want to think of a sequence as a function. And then let's take the hypothesis first that it's bounded. Okay, so if that's a bounded sequence, well then by definition, that set E is a bounded subset. And the completeness axiom of the real line says that, that any set that's bounded has a least upper bound. It has a soup. All right, so let's let L equal the soup of that set E. All right, and then as it was stated in the theorem, we're going to prove that this sequence Sn converges to L. So I'm going to do it with the epsilon definition, so you're not surprised that my proof starts by saying let's let epsilon be an arbitrary positive number. Okay, and by a property of supremum, if we subtract epsilon from L, if we subtract epsilon from this soup, by a property of supremum, there has to be some sequence term, some element of E, that's strictly bigger than that L minus epsilon, right? That's something we haven't talked about in a while from chapter one, but remember, if you back up from the soup at all, then you have to find an element of your set that's in there. Cool. If you want to kind of have some imagery, I'm going to kind of pollute my nice proof here, but if I kind of just draw a little number line, I don't have a lot of room over here. Here's my L. Maybe here's where I'm visualizing L minus epsilon. Because L minus epsilon is less than L, then I have to be able to find an element of my set, that is a sequence term, that is bigger than L minus epsilon. Notice that I drew that term less than or equal to L, but that's of course true because L's the soup, right? That sequence term is no more than L. L is greater than or equal to all these sequence terms. So as I've drawn in my picture, that number, that sequence term, S sub capital N, it lives between L minus epsilon and L. It could possibly equal L, but it has to be strictly bigger than L minus epsilon. Nice. Well, now I'm going to use the non-decreasing part. Okay, so if you take any index bigger than that capital N, this sequence is non-decreasing. So the corresponding sequence term, S sub little n, has to be at least S sub n. So if I draw that in here, if I take any n bigger than or equal to n, that sequence term S sub n has to be greater than or equal to S sub capital N. Of course, it's also still less than or equal to L. L is greater than or equal to all the sequence terms. Okay, so this tiny little picture off to the side is actually becoming handy because it sort of already shows me that for n greater than or equal to n, all these sequence terms are within epsilon of my limit of my number L. So all I have to do is kind of write down the inequalities to prove that, right? What is the distance between these numbers, L minus epsilon and epsilon? Well, that distance is epsilon. And all the sequence terms any n greater than or equal to n have to lie in that interval. They have to be between S sub n and L. So in particular, they have to be closer to L than epsilon. The distance between them has to be less than epsilon. So how does the algebra look? The picture is going to kind of fly off the page, but here, if we write it down, what have we got? We just have to put these inequalities together. We said that S sub little n is at least S sub capital N, which we've already indicated was strictly bigger than L minus epsilon, but everything is less than or equal to L, and that's certainly strictly less than L plus epsilon, right? So what have I got? If n is greater than or equal to n, I've got my sequence terms between L minus epsilon and L plus epsilon. That's certainly equivalent to S sub n minus L being between negative epsilon and itself, or epsilon, which is in absolute value form that statement. All right, so by definition, the sequence converges to L. And let me just remind you that L was the soup. Well, I'm just going to say it out loud. L was the soup of the sequence terms. So that completes that case. If our monotonic, in this particular case, non-decreasing sequence is bounded above, then the sequence converges to the supremum. So in particular, it's convergent. So we'll finish the proof by looking at the unbounded case. If the sequence Sn is not bounded, well, by definition of not being bounded, that means for any positive number m, you can find some sequence term that's bigger than it, right? It's not the case that all the sequence terms are less than some m. So for some m that's positive, or excuse me, for any m that's positive, I can always find a sequence term that's bigger than m, right? But again, this is a non-decreasing sequence. So if you take terms with bigger indices than that capital N, well, the sequence terms are bigger than S sub n. So if you stitch those things together, what do you get? You get for every single index greater than or equal to capital N, the corresponding sequence term is bigger than m. And that, since m was an arbitrary positive number, is exactly the definition of what we mean by diverging to infinity. Okay, so if your non-decreasing sequence is not bounded, then it can't have a limit. It has to diverge to infinity. Nice. So that's the end of the proof. I'm going to leave part 2 of the monotone convergence theorem to you. I hope you'll do it. If nothing else, it's an excellent exercise in kind of reminding yourself of the technical details of, infimums, not being bounded below, diverging to minus infinity, right? So the proof I just gave is basically a roadmap to do it. You just have to, as they say, make the appropriate changes. Okay, so I'm going to end with an example. We said above in example 3 that this recursively defined sequence from your homework was bounded at increasing, and so it has some limit. The monotone convergence theorem says it has a limit. Well, what's that limit? Right? Well, it's the supremum of the set of values, but okay, well, what's the supremum? How do I calculate the supremum? Just because I have a set that I know is bounded, I know it has a sup, it doesn't mean that I necessarily know what that sup is, right? I know that sup is less than or equal to 2, because in your homework problem, you prove 2 is an upper bound, and the sup being the least upper bound is going to be less than or equal to any other upper bound, but how do I know what the sup is? Okay, so this is kind of an algebraic technique you can use. If you know the sequence has a limit, okay, then you can use limit laws to kind of manipulate that. So let's take our recursive equation. Let's take our recursive equation. I'm just going to square both sides of it to eliminate that square root. That wouldn't even be necessary if we had some results about limits of square roots, which I think was an exercise, but I don't know. I'm so bad at keeping track of what I ask you guys to think about. But here I digress. So just square both sides. So you can write that recursive equation as xn squared. And then take the limit of both sides. We know that xn has a limit. So here I'm using limit laws. I didn't kind of dissect them all, but I can kind of point as I use them. If xn has a limit, then so does its square, right? That was from the algebraic properties of limits. Xn minus 1, I mean, those are the terms of the same sequence. They're just kind of indexed one behind. So it's got a limit. It's It's also equal to L. And 2 is a constant sequence. It has a limit. And sums of sequences that converge, everything has a limit. So said very briefly, like I would in a calculus class, take this equation, xn squared is 2 plus xn minus 1, and take the limit of both sides. All right, so here I've kind of notationally written it. But now using limit laws, I'm not going to delineate all of them. Maybe that's a good exercise for you. How many limit laws am I using and precisely which ones? The left-hand side of this would converge to L squared. The right-hand side of it converges to 2 plus L. Oh, I just noticed I already wrote the word limit laws. Lost in my own notes. All right, so I still don't know this number L, but I've done something that's kind of useful. I've found an algebraic equation that it has to satisfy. Classic mathematical trick. I'm looking for a number. I can't find the number directly, but I can find some equation that the number has to satisfy. So if somebody taught me how to solve such equations, I'm in luck. I can find the number. And for me, I am in luck. Somebody did teach me how to solve such equations. I'm going to rewrite that equation as kind of the zeros of a quadratic polynomial. And then I'm going to go ahead and factor that polynomial. I'm going to just write that without comment. And then by the property of the product of two real numbers being 0 means one of them has to be 0. The two possible solutions to that equation are 2 and -1. All right. Well, I'm kind of trying to talk you into the fact that our limit is 2. So how do we rule out -1? Well, I'm going to use some order properties of limits. Okay, every term in our sequence is positive, or excuse me, more precisely, non-negative, actually positive. So if you like, you can ditch this. Xn is greater than 0 for all n. I don't really need to dwell on that. So by one of our order properties applied to xn and the constant sequence 0, notice how the strict inequality here has to be a possibility, but the limit of xn has to be non-negative. All right, so that rules out -1. -1 is not greater than or equal to 0. So our sequence converges to the number 2. Cool. All right, that brings us to the end of the video lecture. Thanks for listening.